Architects don't need to know quantum physics. This doesn't seem like a particularly deep insight, but I'm hoping to convince you that it's very profound, indeed one of the biggest mysteries of science. And a recent paper made a pretty good step to solve this mystery. Let's have a look. For all we currently know, everything in the universe is made from 25 elementary particles held together by 4 forces. This sounds, let's be honest, somewhat boring. But out of these 25 building blocks, the universe has created a bewildering variety of structure. Galaxies, bacteria, planets, hurricanes, humans, societies, cat memes. Far from boring. The universe creates complexity out of simplicity by a process we call emergence. Loosely speaking, emergence means that small objects collect into larger ones, and the larger ones follow new natural laws in their own right. That's loosely speaking. Strictly speaking, we don't know what it means. And that's the problem. Emergence is the reason why architects don't need to know quantum physics. The laws of statics emerge from quantum physics. The details of the individual particle's quantum behavior don't matter. Emergence is also the reason why we can talk about the orbits of planets without knowing exactly what they're made of. And emergence is also why a degree in particle physics doesn't make you a good heart surgeon. Physicists call this the separation of scales, that we can talk about different laws of nature at different levels of resolution. On the deepest level, on the smallest distances, we have the standard model of particle physics. When we go to larger scales, we get atomic nuclei, atoms, molecules, materials, and eventually human beings and their troubles. The interesting thing is now that the most complex systems that we know, humans or human societies, do not have this clean separation of scales. If you take drugs, then tiny molecular reactions will affect the entire body, and that in turn can affect other people. And the other way around, humans have built big particle colliders that affect what's going on at much shorter scales. To use a somewhat simpler example, the Earth's weather and climate depends on the physics of many different scales and actually mixes them together. Somehow, this mixing of scales seems to be essential to complexity. This is why understanding emergence is the key to understanding complexity. When it arises, why it arises, and what we even mean by it. And in the new paper, a group from the University of Sussex put forward a mathematical definition for emergence. They quantified the independence of large-scale structures from the underlying details in 2 ways. One is by using what they call causal closure among a group of properties. This basically means that you can formulate natural laws on one level of resolution without needing input from the underlying detail. A good example is a computer. You can explain the logical flow of a computer algorithm without knowing what the computer is made of that the algorithm runs on. This is why some people think that computer science is in some sense more fundamental than particle physics. Usually these people are computer scientists. The other idea in the new paper is to ask how redundant the details of the underlying structure are. Say you want to make a traffic flow prediction. You don't really need to know exactly where each driver came from and went to. You just need certain classes of typical drivers, daily commuters, occasional shoppers, long-distance through traffic, and so on. And if you do that, you'll still get the correct prediction. To put this differently, you can lump together many drivers into certain classes. Traffic flow is highly lumpable, and the more lumpable a process is, so the idea, the more it's causally closed. They call this property lumpability. I'm not making this up. This is really how they call it. They then use these 2 notions of emergence to quantify emergent properties in some examples. One example that they use are cellular automata. A cellular automaton is a simple algorithm in which a line of pixels is updated one by one according to a simple rule. The fascinating thing is that some of these rules give rise to very complex patterns. In the paper, they show that their formalism correctly identify some features in these simulations as emergent, which is pretty cool. They also look at numbers built up of pixels. These numbers form new objects in their own rights, which can then be used to, say, describe whether statements are false or true. I find this to be a very interesting development that can have a lot of applications, especially in artificial intelligence. But there are many other cases where this could be useful. Think of identifying weather systems or activist groups. Emergence is really everywhere. If you take one thing away from this video, it should be that lumpability is a technical term. Instead of complaining that men are all the same, I shall henceforth say they're highly lumpable. I got several questions this week about a few headlines that said something about a new study that challenges dark matter, and that it's possible to create gravity without mass. That sounds very interesting, so I had a look at the paper. The idea in the paper is based on a peculiar property of gravity that you might have heard of but forgotten, so maybe let me start with recalling it. It's that inside a hollow sphere there's no gravitational attraction. This is already the case in Newtonian gravity, but it's also true in Einstein's theory of general relativity, even though in this case one strictly speaking has no force. That there's no gravitational pull inside a hollow sphere is a matter of geometry. Suppose you're near this side of the sphere. The gravitational pull of the mass closest to you has the strongest pull. But there's more mass further away from you, so which one wins out? Well, if you add it all up, you find that the total gravitational pull is exactly zero. It's like when people complain about me on Twitter, it averages out to zero. To explain dark matter with this, the author of the new paper proceeds roughly as follows. Suppose you not only have positive mass, but also negative mass. Yes, there's no negative mass, so this is kind of like saying suppose you have a laser-eyed unicorn. But let's leave this aside for now. I'll come back to this later. So let's just assume some matter with negative mass exists somewhere out there. Now, for the gravitational force, mass plays the role of a charge, like the electric charge for the electric force. You can see this if you compare Newton's law of gravity with Coulomb's law for the electric force. The masses act like charges. The difference is that for the electric interaction, like charges repel and unlike charges attract. For gravity, like charges attract and unlike charges repel. To come back to the paper, we now put a shell of negative mass inside a shell of positive mass, but so that the total mass is zero. Since the total mass is zero, the gravitational pull outside the two spheres is zero. We also know that the gravitational pull inside is zero because it's a sphere, but between the two spheres, the gravitational pull isn't zero. Now suppose you have a normal positive mass moving towards the shells from the inside. It feels no gravitational pull until it reaches the innermost shell, then it gets repelled by that negative mass behind it and attracted by the one ahead. Then it passes through and there's no gravity anymore. The result is that it was accelerated. Now you have to imagine that you move these spheres towards each other until they sit right on top of each other. You then have a solution that has no mass because the negative and positive masses cancel each other out, but that generates a sudden acceleration. Perfect for those days when you have trouble getting out of bed. If you were to do the maths of the example that I just gave, it wouldn't work. What he does in the paper is somewhat more complicated, but the gist of it is the same. No total mass, but a sudden acceleration. So this is where the idea comes from that you can have gravity without mass. It's because you have both positive and negative mass together on the shell. How does this help with explaining dark matter? Well, remember that one of the observations that we usually attribute to dark matter is that the outer parts of spiral galaxies rotate too fast. Yes, this is also the case for the Milky Way. You see, the velocity of a star in its orbit around the center of a galaxy is determined by the gravitational pull that comes from the matter inside the orbit. The higher the gravitational pull, the faster the star needs to go to stay in that orbit. It's kind of like you need to pedal faster on your bike the more snacks you've eaten. The author of the new paper now says there are like 1 billion or so of these no-mass shells inside of galaxies, and they gradually increase the acceleration as you go further to the outer reaches of a galaxy. So it looks like dark matter, even though there's no mass. You might think that the obvious problem with this idea is that we've never seen any particles with negative mass. And yes, that's that. But I think it's not any worse than dark matter, which we've also never seen, have we? Maybe negative mass is out there, we just haven't measured it yet. And let's be honest, dark matter is so mainstream now, it makes poor headlines. No, the major problem is the stability of these shells. Remember that for gravity, like charges attract and unlike charges repel. If you push together like and unlike, they'll not stay on the shell. They'll want to separate. And they'll also not stay in a shell, of course, they'll try to clump. It's a long story, but I tried something very similar about 10 years ago. It didn't work. Now, it's quite possible that I'm missing something and I think this is a nice idea, but I'm rather skeptical that it'll work. Though I must admit I'm very tempted by getting a pair of anti-gravity shoes. I've been talking about AI so much I've almost forgotten to look at what's going on in quantum computing. But the funniest thing happened. Remember that a few weeks back I told you about what I thought was the most impressive quantum computation at the time. A chief scientist at that company now accidentally claimed that this calculation could be done better by a non-quantum computer. So now what? Quantum computers are useless after all? I have the summary. Quantum computing, so the fairy tale goes, is the next big thing in technology. Any nation that likes to think of itself as advanced has poured crazy amounts of money into it. I think that quantum computers will remain niche applications, and most of that money is wasted. But then I'm just a cranky woman with a YouTube channel, and there are more intelligent people deciding what to do with your taxes. The news today is about a battle between two fundamentally different ways of doing quantum computations. The one is what's called a universal quantum computer, or sometimes a gate-controlled quantum computer. It works very similarly to conventional computers. A conventional computer uses bits, a quantum computer qubits, but in both cases you execute algorithms by acting on those bits or qubits. Universal quantum computing is what most quantum computing companies are after, including Google, IBM and Microsoft. The other approach is a quantum annealer, sometimes called a type of quantum simulation. A quantum annealer is more like an analog computer. You set it up so that it answers a particular question, then you let the system follow the laws of nature. The best and biggest ever quantum simulation to date comes from the company D-Wave and just dropped 2 months ago. They calculated how a lot of tiny magnets would interact, which is a computationally extremely difficult problem known as the Ising model. They then estimated how long it would take to do this calculation on the best current supercomputers. As an example, they used the Frontier supercomputer located at Oak Ridge National Laboratory in Tennessee. They said that a calculation which took them less than a second would have taken more than 1 million years on the Frontier supercomputer. That's pretty impressive because so far all other claims that a quantum computer could do something a conventional computer could not do at least as fast have evaporated. It's really big. The news now comes from a company by name Q Control in Sydney. They don't build quantum computing hardware, they focus on software development. In a new paper which just appeared on the archive, they say that they have come up with an algorithm that does the D-Wave calculation on an IBM quantum computer, so a universal quantum computer. For this, they use the IBM Eagle with 127 qubits. They say their implementation of the calculation calculation actually works better than that from D-Wave in the sense that it produces results in a similar time, but with better accuracy. You can see why D-Wave wouldn't like that. It makes them look less special. So Trevor Lanting, the Chief Development Officer at D-Wave, declared on LinkedIn that there is no threat to D-Wave's leading position in quantum optimization. So far, so obvious, you might say, but figure this. The reason he says that the new calculation is no threat to their leading position is that the new algorithm is not properly a quantum calculation, but that, quote, the work is done by a sophisticated classical algorithm. I know this is all heady stuff, but you see, if this was correct, then he'd just have admitted that one doesn't even need a quantum computer to do their calculation. Why would he do that? One of the authors from the Q-Control paper was similarly confused and pointed out that actually this isn't correct, that it is indeed properly quantum. Okay, so that was kind of confusing, but what does this all mean now? It means basically that universal quantum computers aren't as far behind quantum simulators as we thought. The Q-Control papers say basically with the right algorithm they can do it better. In a nutshell, IBM is back, basically. Until, of course, someone else shows that they can indeed do it on a conventional computer. This is the latest iteration in a long series of claims that someone has outperformed someone else until someone else shows that this was not the case. I actually think this constant drama is a good development. Not just because it gives me something to talk about, but also it demonstrates how competition is advancing the field. Though that said, in the end it doesn't really matter all that much who is a few seconds faster, but who can do it for less money. So really I think the metric they should be using is dollars per digit. I recently read that the world has crossed 1.5 degrees of warming above the pre-industrial level, the limit set in the Paris Agreement. Then I read that we crossed it several years ago. Then some climate scientists objected. Then I read that the average temperature in 2023 was 1.56 degrees above pre-industrial, but that this doesn't mean we have breached the 1.5 degree threshold. So now what? Have we or have we not breached the threshold of the Paris Agreement? That can't be so hard to answer. I've had a look. Last year in November, the climate scientist Jim Hansen called the Paris goal deader than a doornail and said that anybody who understands the physics knows that. Another climate scientist, Michael Mann, said in response, I've got 3 degrees in physics and I can tell you that Jim is wrong. In January, a Nature comment vaguely said that 1.5 degrees are approaching. In February, headlines declared we had crossed the 1.5 degree threshold. In case you still aren't sufficiently confused, here's how the climate scientist Michael Mann recently tried to explain this.
So here you could see the zero. That's not quite the true zero here because there's already been warming. But on this scale, 1.5 C is this where my cursor is. The black curve remains below 1.5 C. So the baseline here, you can quibble over what the right baseline is. So let's not worry too much about that. If we say that 1970 is sort of where we were was our baseline and we're measuring relative to that, then 1.5 C is this tick mark and this line, this horizontal line here. And so basically it's like 2035 or so. If you extrapolate the curve, you use actually a more rigorous baseline. This isn't quite the right zero. If you use the right,
isn't that way off? We're talking about late 1800s and you're using 1970. What am I missing here? That's
there's been
there's like half a degree or something, isn't it? That how much?
Let's see if we can.
That means we're already way over. 1.
No, we're not. Here, let's get the.
Relative
this is relative to a 19. So this is relative to a 1900 to 2000 baseline.
Right.
So it's slightly elevated, but not hugely.
Well, that means 50-ish kind of number, right? Yeah.
We are at relative to the official late 19th century baseline used by the IPCC. Right now, we're at about 1.3, between 1.3 and 1.4. That's what the numbers say.
And this,
So if at
okay, I'm
1.3
confused now,
between
but-
one
So the warming is between 1.3 and 1.4 degrees, but the baseline isn't so important? Well, of course the baseline is important. The baseline is what you compare the current temperature to. For the Paris Agreement, one usually compares the current temperature to the pre-industrial average. That's 1850 to 1900. By the 1970s, we already had more than 0.2 degrees of warming. If you add the 0.2 to 1.3, then that's more than 1.5. Or is it? I mean, if 1 times 1 equals 2, maybe 1.3 plus 0.2 is less than 1.5. What do I know? Oh dear. But don't despair, we can figure it out. The first thing you need to know is that some headlines about crossing the 1.5 degrees limit were about a paper published in Nature Climate Change in February. That paper, however, compared today's temperature to the average in the 18th century. That is much earlier than the usual pre-industrial baseline, which is 1850 to 1900. They were arguing that the warming in the 18th and early 19th century was also partially caused by humans. And the Paris Agreement doesn't specify according to which baseline to calculate the 1.5 degrees. So if you interpret it to refer to the 18th century average, then we have crossed the threshold. That explains part of the disagreement. While I can understand that one can debate what pre-industrial might mean, the 1850 to 1900 has become the norm, so it makes sense to stick with this. Let's therefore ignore this paper. It's just causing confusion. To sort out the confusion that man caused, let's have a look at this figure, which has the right baseline. You see here the black line, that's the data, and the yellow shaded area, that's the model projections. And this is 1.5 degrees above the pre-industrial level, so that's the Paris threshold. You see that we have clearly crossed this last year. And this happened according to multiple different data sets, which makes it hard to put it down to some measurement issues. If that's so obvious, why is there even any debate about it? It's because the Paris Agreement doesn't say how the 1.5 degrees of warming are to be calculated. And it's generally acknowledged that if the threshold is broken during only 1 year, that's not sufficient evidence. This is because the Earth has natural temperature fluctuations on longer durations, most importantly the El Niño Southern Oscillation, ENSO for short. That's a few years long. It's because of fluctuations like this that the IPCC uses a 20-year average. But if you want to calculate a 20-year average for any particular date, you need to have data 10 years to the future. This means even if we cross the 1.5 degree threshold this year, we wouldn't know until 2034. This is why in the Nature comment from January, the authors suggest using what they call a projected 20 years average. They say, let's use 10 years of data from the past, a 10-year projection from the models, and then average that. This also explains, I think, what man was talking about. Let's look at this figure again. The 1.3 degrees warming that he was referring to is probably this projected 20 years average. You can eyeball this here by averaging the black curve. This puts the current average at around 1.3 or so above pre-industrial, and we would cross the 1.5 degrees threshold between 2030 and 2035 or so. Though if you look at more precise predictions from the models, it might happen as early as 2027 or as late as 2037. So in summary, yes, the 2023 average temperature was more than 1.5 degrees above the pre-industrial level. No, this doesn't mean we have broken the Paris Agreement, because the 20 years average is still only 1.3 degrees or so. But yes, Hansen is right, of course, that the Paris goal is deader than a doornail, because we'll blast right through it. Really, I can't think of any better example for how much of a mess science communication is than that. Thanks for watching. See you tomorrow.